I called for this meeting so we can discuss the current efforts that are going on to enhance Rebalance. There are a lot of different efforts that falls under this general title. So I think it will be good that we will all have the same view of what's going on, so we can all contribute and participate in this effort. This session has quite a bit of content. I didn't think there would be so much content when I started preparing this presentation, but as I went on and on, I saw that there is a large amount of content. I'm not sure we can cover all in one session because I don't want to rush through this. I want people to really understand the processes. So let's start and see until what point we can go to. And in case we will need, we can have a follow-up session to finish going through the things. So basically, we will have 6 sections. The first section will talk about the current design and implementation of Rebalance and what drawbacks result from these design and implementation decisions. In the second chapter, we will briefly discuss global layout and how it helps to solve some of the mentioned drawbacks that I will mention in chapter 1. Chapter 3 will give an overview of the roadmap of the changes. As I mentioned, there are several changes. So what are the dependencies between the changes and what is the plan? In the fourth chapter, I will go more in depth into some of the changes that I already started making, mostly on the rebalance part of things. There are 3 sections in this single section. Chapter 5 will talk about an enhancement basically to the global layout itself, which is a bucket model, which is an even more advanced distribution model, also very in brief. And for the last chapter, we will see how we can best progress with these efforts. So I think we can begin. As I said, the first chapter, we will go over the current design and implementation of Rebalance. So basically, what is Rebalance and how does it work? Rebalance is mostly used in order to evenly distribute data across the server nodes in case we change the number of the nodes in the cluster. When we add fresh nodes, we want to distribute the nodes and distribute the load of the data and move some of the data to the newly added nodes. Or in case we shrink the cluster, we want to migrate the data between the nodes that we plan to remove to the nodes that will remain. So this is the major usage of Rebalance. A smaller one is used to migrate data after performing a rename, because the rename itself produces something that's called the link file, but it doesn't actually migrate the data. So Rebalance is also used to migrate the data in this case. And let's jump into the internal of the process. In the heart of the process, basically Rebalance is a producer-consumer process, where the producer is a single thread that traverses the file system recursively and performs several operations as it goes. In the forward step of the recursion, we perform a reader operation on the tier that we are currently in. And in this first reader, we ignore all file entries, because we will have a second reader operation that will handle file entries, but in this point in time, we ignore them. And we only handle dir entries. Each dir entry that we find, we go into and perform, again, the forward step of the recursion, this reader operation. Once we have reached the most nested deep in the dir tree structure, we start returning back. And as we return back, we perform a couple of operations. The first one is a fixed layout operation, which calculates and assign the new hash ranges across all the nodes. And we will perform a second reader operation. And this second reader operation we will perform in a round-robin manner on the local subvol. The first reader operation went through the volume itself. The second reader operation will be performed on the local subvols, which are local to this node. And in this reader operation, we will queue the dir entries that we find. We will ignore the, we'll queue the file entries that we find, and we completely ignore the dir entries. So notice the difference. In the first reader operation, we ignore file entries and we handle dir entries. In the second reader operation, we ignore dir entries and we handle file entries. So in this step, we will add all the dir entries that we find into a queue. And now let's jump to the consumer side of the process, because until now we discussed the producer side of the process. So the consumer side of the process are several threads that we can call them migrator threads that in the background dequeue file entries from this file queue. And will perform migration as needed. They will check if the files are in their correct position after the change of the layout. And if not, the migration will be performed as needed. Any questions up until this point on the general process? Everyone has an general understanding of what's going on?
Yes.
Yes, please.
Yes, correct.
No, we have the understanding, yeah.
Okay.
We have the understanding. That's what the yes meant.
Okay.
Okay.
So I prepared a visual representation of the process that will also help us to jump into the code, because I plan to do a code walkthrough as well. So this visual representation also mentions the relevant methods by name and what is their process. Maybe it's better if I make it, yes. So we start rebalance in a method that's called defrag start crawl, which basically this method performs some initialization and some operations that are needed to jumpstart the process. And this is performed by the main thread. In this main thread, we will also spawn the worker threads, which are the consumer side of the process as we discussed. And these threads later on will dequeue the file entries, but let's hold on this for now. So the main thread, after it finishes initializing the process, will jump into the recursive method that does the several operations that we just mentioned. It will perform the first reader operation to go more deep into the nested dir structure. And on the way back, it will perform the fixed layout as a part of this method. Once the part of the fixed layout is done, it will call a different method that's called defrag process dir, which round robins the local subvols. And inside this one, we have another method that's called defrag get entry, which performs the second reader operation and queue the file entries into the queue. Which in this point, as we said, we have the migrator threads from the other side, which dequeues entries and perform migration as needed. So in a very briefly overview, this is what rebalance looks like visually. What are the drawbacks of this model? First of all, one of the most major drawbacks is the need for a fixed layout operation. And fixed layout operation is performed for every dir in the file system. So as you can understand, we perform this operation a lot. And this operation has several problems. First of all, it's very log intensive. In order to calculate and assign the new hash range, we basically need to log the dir instances across the entire volume. And not only do we need to log them, we need to log them in a very specific order, because rebalance in the end is a process that is local to a server. So we have one rebalance process per server, but this rebalance process also needs to take into account the other nodes, of course. So the reason that we need to log the servers in a specific order is to avoid the condition of a deadlock. Let's say, for example, we have 5 nodes in the cluster, and rebalance the process number 1 starts locking from node number 1 to node number 5, and rebalance process number 2 will try to lock from server 5 to server 1. So in the end, they will collide and we will have a deadlock. So the locking operation needs to be done in a specific order, which makes this process even more expensive. Due to this fact, we are forced basically to traverse the file system in a single-threaded manner, because everything that I just discussed in this lock-intensive operation will be multiplied by the number of threads that we have that will scan the file system. So as we mentioned, we traverse the file system single-threadedly, so this is the reason for this. And another drawback is that we need to perform the reader operation twice, because if you remember, in the first reader operation, we only handle tiers, we ignore the files. In the second operation, we only handle files and ignore the tiers. And as you know, reader operation is not exactly the fastest operation in Gluster, so the fact that we need to perform this twice is basically a drawback. So all of part 1 of what is mentioned here is drawbacks that are related specifically to the fixed layout operation. Apart from this, we have a drawback that is resulting from the distribution model itself, that we have a lot of files that are being migrated between nodes that are already existing in the cluster. Ideally, for example, if we expand the volume, we would only want to move files from the nodes that are existing in the cluster to the new node. We don't want to move files between the nodes that are already existing because it doesn't contribute to us anything. So all these files are basically a wasted effort. And this is a result of the distribution model itself that needs to be a continuous layout per server. And we will discuss this more in depth later. Another drawback is it blocks the design and implementation of more advanced distribution model, for example, the bucket model that we will also discuss more in depth later. And all of these things that are mentioned here basically adverse scalability and flexibility, because I think the UI of Gluster is very good. It enables to perform all these operations one command in the command line and it's done. But there is a cost to this command. So rebalance can take, if the cluster is big, rebalance can take a very, very long time, weeks, and I even heard months coming up in some discussions. And it adversely affects scalability and flexibility, and obviously the bigger the cluster, the bigger the problems. At this point, let's do a quick code walkthrough so we can go over what we just discussed. So as we mentioned, the entry point for the rebalance process is a method that's called defrag start scroll, which performs some initialization. In this method, we perform simple things such as look up on the root tier, make sure it's there. We perform the fixed layout operation of the root tier. I won't go into details into all what is going on here, just the main parts that I described in the diagram. So here, basically, we start the migrator threads, which are the consumer side of the process. I will get back to this later, but I want to start with the producer side of the process. So if you remember, the fixed layout method is one of the core components of the process. In here, we perform the recursive call and the first reader operation. So we have a loop on the reader operation as long as we have entries. We ignore all the file entries. If it's a file entry, we just continue in the loop. If it's a dir entry, we will perform some operations on this dir. Again, make sure it's there, some basic checks. And we will perform a recursive call here. Once we are done with the recursive part of the process, this loop will end and we will start going back. And the first thing we will do is the fixed layout operation. It's not mentioned by name fixed layout operation because it's a set exater operation, which internally triggers the fixed layout operation. But this itself can be considered as a fixed layout operation. Once the fixed layout operation is performed, we will call a method that is called process_dir, that, as we mentioned, performs the round robin processing of the subvols. You can see that we traverse all the subvols, and inside here we have a call to get entry, which is here. And inside here, we will perform the second reader operation. And in this case, we will ignore all the file entries and we will only handle, we will ignore all the dir entries and we will only handle file entries. And whatever file entry, here you can see that if it's a dir, we ignore it. If it's a file entry, we will basically queue it to the queue. Let me find where exactly this is performed. Okay, so here we get the actual file entry, and here we queue it to the file queue. So basically, at this point, the producer side of the process is complete. So let's go back until we reach the initialization stage, which is the start call method, and look at what is happening at the consumer side. So we initialize some threads, migrator threads, to perform the migration. All of them perform a method that's called gf defrag task. And inside here, you can see that we dequeue a file entry. We dequeue the file entry, and we perform the migration. We check if migration is needed and perform the migration. I won't go into details into what is going on inside here, because this is not much changed in this set of changes that we will discuss later. I do want to highlight one thing that is being changed, is how do we make the decision of whether or not to migrate file. So basically, the decision if to migrate file or not is performed here. We calculate the hash subvol and the cache subvol for the given file. If they match, then we don't need to do anything, so we don't migrate the file. If they don't match, then we migrate a file. And the key thing inside here is that we calculate the hash subvol using the inode of the parent directory. We get a layout of the parent directory, and based on this, we basically calculate the hash subvol. So this will change later on, so I just wanted to highlight this part. Any questions regarding the code walkthrough? Something is not clear?
Okay, so I have one doubt, Barak. There is a concept of commit hash that is happening after each of the fixed layout and the migration, right? What is the significance of that?
Basically, the commit hash is what version of layout we are currently in.
Okay.
Yes, please.
Yeah, so I was just wondering why it is set only on the root of the volume and not on the other directories. Is there some significance for that?
Let's see. I'm not sure about this part, but let's see if we can figure something out.
Because I think this also kind of affects the global layout, I believe. I could be wrong. I mean, like, it is what I read. At the end of fixed layout and migration, I think it is trying to do a commit hash at the end. I didn't understand. So it tries to do something like new hash mode or something like that. It will do a setxatter, and dhast actually is taking that and figuring out some new hash mode, and it is actually setting that on to the root of the volume. It's okay if you didn't get a chance to look at it. We can discuss it after this uh, recording also. I'm like, whenever you get a chance. It's not super urgent or anything, but that is something that I didn't understand. What was the need for that?
Mm-hmm. Basically, from what I know, the commit hash is what version of layout we are currently in, because we can update the layout multiple times. In each rebalance, we will update the layout once, but the layout itself over time can be updated multiple times. And I think this is some mechanism to make sure that we are that all the tiers across the volume are in the same version. And from what I understand, also we only commit the hash if there were no errors during the migration of the file in this directory. Whether it affects global layout, I don't think it should affect global layout in any way, because basically what we do in the per dir model for every dir, in global layout we do once. So this, let's say, general logic doesn't change, but I will need to take another look at this offline to get more into details of this.
That would be great. Thanks, Barak.
Mm-hmm. Okay, so let's jump into the next chapter, which covers global layout, just a brief overview without actually going into details. So basically, what is global layout? Global layout offers an alternative distribution model. In this model, a layout only exists for the root directory. So instead of having a layout for every directory in the volume, we'll have a layout only for the root directory. And in order to implement this, we need changes both on the client side and on the server side. So if we're talking about the client side, basically we need to remove all allocations of layouts for all the tiers except the root, because they don't exist in this model, they are pointless. And modify the way that we perform hashing on a file, because currently we perform hashing using the file name only. And this works fine in the per directory model, because the, let's say, randomizing factor, it already exists on the dir level. But since global layout, we can sort of think about this as all the tiers in a given node has the same layout as the root tier. So hashing only by the file name is not good enough, because it will result in all the files having the same name existing on the same node. So if, for example, I have a file called 1.txt on the root tier, and in the root tier I have tier 1, and inside tier 1 I also have file 1.txt. So if file 1.txt that existed on the root tier is hashed to subvol 1, then all the files with the same names inside the root tier will be hashed to the same node, which is not a good enough randomizing factor. So one of the main things we need to do on the client side is modify the hashing mechanism itself. And based on previous discussions, a couple of alternatives came up, either using the GFID itself as a hash, because the GFID is completely random. Though I remember previous discussions mentioned that some other supporting mechanism needs to be implemented in order to make sure this approach works in a good way. And another alternative that came was use a combination of the file name and the GFID of the parent directory to create a hash. And on the server side of things, we need to modify the decision-making mechanism to determine whether or not files need to be migrated, as I mentioned, not based on the parent directory layout, but based on the layout of the root tier, because the layout only exists on the root. Any questions regarding this high-level overview? I will take the silence as a no. And basically, Several of the disadvantages that we mentioned in the pair directory distribution models are eliminated by the global layout model. And the first one is the need for a fixed layout operation, which is completely eliminated for all tiers except the root tier, which is a huge benefit because, as we discussed, this is pretty expensive and limiting operations. And by eliminating the need for a fixed layout, we open the way for multiple enhancement in Rebalance, as we will discuss in depth later. And in addition, it opens the way for the design implementation of an even more advanced distribution model, which is the bucket approach, which this model eliminates one of the key drawbacks that we currently have in Rebalance, which is the inner file migration between pre-existing nodes. And the result of all of this, we positively affect both scalability and flexibility. A couple of words regarding the upgrade path, because obviously this is a very important aspect of making substantial changes. So when we want to upgrade from the per tier model to the global layout model, both clients and servers need to be changed. Now we need to differentiate between two upgrade scenarios. The first upgrade scenarios deals with cluster being able to support volumes both in the old model and the new model. So for example, if a user already has an existing cluster and has some volumes set up, and he wants to upgrade to a new version of cluster which also supports global layout. So the first upgrade path is dealing with the creation of new subfolds in the global layout model, while also supporting currently existing volumes in the old model. So this dual model should be fairly simple to implement. The more complex upgrade path deals with upgrading existing volumes from the per tier model to the global layout model. And this is a bit trickier because simply upgrading clients and servers will result in clients thinking that most of the files are out of their place because we heavily modified the distribution mechanism. So I have some upgrade path in mind, let's say, to how to do this. And I believe it will need to go through some intermediate state, which will help the transition between these two modes. But this is something that definitely needs to be discussed more in depth as this effort progresses. But I just wanted to give an overview, a very general picture of what the upgrade path will require. In this chapter, I will give a general overview of the entire efforts, what main components are in this effort and the subtask that requires in each of them, at least the subtask that I already started to handle. Yes, please.
Should I interrupt you right now with a question or at the end of the meeting?
Yes, please, feel free.
Yeah, so in the global layout, right, if we just do it for the root directory, right, then there is a possibility that, let's say, one of the nodes is, having more data and the other node is having less data because one of the directories in the root directory was consuming too much of space and the other was not consuming that much of space. So is only root doing that a good idea, or going at least up to 3 levels would be a better thing? I was just thinking about that, that is the first challenge that you might encounter. I mean, that is what I feel.
Can you explain why the root directory is special in the sense that one node will be more loaded than the others?
Yes. Let's say, if people are using Gluster in a scenario where they are storing the ISOs for the virtual machines, right? and one of the directory contains ISOs, the other directory contains some other information that is not ISOs, right? And the ISOs being the heavy file, right? And if we are just scanning the root directory, let's say the root directory contains 3 directories: ISOs and code and let's say documentation, right? Now ISOs being the heavy one, right? If we are just going to um, uh, uh, create a hashing out of its name or something, the root parent directory, the file name and the parent directory's GFID, will most of the files go into one server, and the let's say in our distribution model, it's a replica volume and we have 3 nodes. So all the ISOs in one node and all the code in another node and all the documentation in third node. Will that be the case, or will it be, evenly distributed with? So I mean, that just came up, so I thought,
Yes, I understand your question, and this is exactly the purpose of this section 3.1.2. In order to ensure that we keep evenly distributed data, we can't rely on a hash that is based on a file name anymore, because this will result in affinity with all the file names that have the same name to go to the same node, which is obviously not the case we want. So in order to avoid this scenario and make sure that we keep distributing evenly as we distribute evenly now, we need to modify the hashing mechanism.
okay. So that point you had, I mean, maybe I didn't understand it much that time, but that point is taken care of, right?
Yes, we will keep distributing data evenly as we do now.
All right. Thank you.
Welcome. Any other questions before I proceed to the next chapter? Feel free.
Yeah, Barak, one doubt. So when we are actually like when the user actually makes the decision to move to the new layout, we will have to remove these extended attributes on the directories, right?
Yes.
So
You
won't that
you can remove
Sorry?
them, or you cannot. You can remove them and you cannot remove them. But if you don't remove them, they will basically be useless. Like no one will use them, let's say.
Okay. So basically we are going to remember in the client that it is new layout at some point and ignore the external attributes.
So basically you are asking about the upgrade path, correct?
Yeah.
So I think what you're asking deals with this point 3 in this slide, which deals with upgrading an already existing volume that is currently operating in the per directory layout model, and we want to upgrade it to the global layout model. Out of the all upgrade passes that exist, this is the most complex one. Because as I mentioned, just a simple upgrade won't be good enough, because it will immediately result in clients thinking that most of the files are not in their place, which will result in a large amount of problems. I still need to give more thought about how to perform this upgrade in the correct way. And this is one area that I definitely can use the help of more senior folks. I have some model in mind, but it's definitely not finalized yet, and I'm not comfortable enough to say that this is the way to do this. This is something that we will need to think about.
Okay, cool. We can discuss about it on GitHub. Thanks.
But the thing that I do want to highlight, if it wasn't clear before, if you already have a cluster running and you have some volumes set up, if now you want to upgrade cluster to a version that will include this global layout model, and you want to create a new volume that will operate in the global layout model, so it will be possible to have in one cluster version both volumes that operate in the per dir model and in the global layout model simultaneously.
Yeah. we are basically maintaining backward compatibility, right?
Mm-hmm. Okay.
Got it.
Okay, so in this chapter, I will give a visual overview of the planned efforts and what each effort is composed of. Well, at least the parts that I already started working on. So the things that we need to keep in mind is that the general title of this effort is enhancing rebalance. We want to improve the performance of rebalance. And this I can split into 3 major sections. The first one is the global layout section, because this enables all the resulting enhancements. So the first one is the global layout. The second one, and this is actually the focus of what we discussed today, is internal enhancement to the rebalance process, which is this section of the diagram. And finally, we have the bucket model, as you can see down. Just I don't want to move the mouse because the thing comes up. And each enhancement is meant to solve a certain type of problem. As we discussed in the beginning, the global layout basically eliminates the need for a fixed layout operation, which opens the way for multiple enhancements. The internal rebalance enhancement basically optimizes the way that rebalance operates. And the bucket model solves the problem of migrating files between pre-existing nodes in the cluster. So the bucket model basically eliminates inner migration of files. And our focus for today, as I said, is the internal enhancement for rebalance, which I have already started working on. So we will touch these 3 sections in depth now in this section. We will do a walkthrough of the 3 parts of the enhancements. So the first part is actually transforming rebalance to work in a global layout model. As I mentioned when we did the code walkthrough, the decision to whether or not we migrate a file is done by calculating the hash subvol using the layout of the file's parent tier. In the global layout model, the parent tier doesn't have a layout, so we need to use the layout of the root tier to calculate whether or not the file needs to be migrated. And this is a very small patch. Basically, it does 2 main things. It caches the layout of the root tier during the initialization phase after the layout, of course, has been fixed. And we modify the decision-making part of rebalance to migrate files based on calculating the hash subvol using the layout of the root tier. Any question about the general idea before I jump in the code? I will take this as a no. So let me switch to the correct branch. And I think I can compare with Devil branch, so we can actually see the changes. Yes. So our main focus is the rebalance part itself. And we will start, I guess I can enlarge this a bit. Again, we start from the initialization method, the start call. I've made some minor changes that I'm not gonna go through in, like naming changes for some dict, because the fixed layout operation is completely eliminated, so this name is not correct anymore. I will only touch the key elements of this change, which, as I said, is caching the layout of the root directory during the initialization phase. And at this point, the layout has already been fixed, so we cache the new layout. And the second major part of this change is in the decision-making process. Before we get to there, let's take a quick look at the recursive method. What used to be fixed layout, default fixed layout, I changed the name because, again, fixed layout is eliminated. We basically eliminate the fixed layout operation here. So we don't perform a fixed layout operation anymore, completely removed. And let's jump to the decision-making process, which I think is here somewhere. Yes. So basically here we look at the method that is performing the migration of the file. And as you remember, this is performed by the consumer threads. Consumer threads DQ file entries from the queue and process them for migration. So in this part, we don't use the layout of the parent directory anymore, but we use the layout of the root directory in order to calculate the hashed subvol. And just to see the implementation of this method really fast, not much has changed. We pass the layout of the root directory, and we use this to calculate the subvol, the hash subvol. Now, if we look at the original method, we calculate the hash subvol by taking the layout of the parent tier and using this to calculate the hash subvol. So this is a fairly small change. Any question about the code itself? I will take this as a no. So we can move on to the second part of this change where things actually start to get interesting, which is parallelization of the way that we traverse the file system. Previously, or in the original code, we traverse the file system single-threadedly because the limitations that we mentioned earlier. So this change modifies the way that we traverse the file system to traverse it in a multi-threaded manner. And the original process was completely recursive. If you remember, we performed the first reader operation, ignored files, and for each tiers that we found, we went into this tier and again performed the reader operation. In this patch, this process is transformed to be part iterative and part recursive. So let's call it a hybrid approach, which I will get into the details soon. One very important thing that I want to mention is part 2 and part 3, which is the next part, obviously, are one logic unit, and both of them need to be looked as one. The reason that I separated this is basically to make reviewing easier because the changes here are pretty big, so it will be overwhelming to combine both of them into one. But things definitely cannot stay in the state of just making the changes that this patch makes. Some things that are worth mentioning. All of the things that deal with the file queue. For example, the elimination of the queue, the second reader operation, are not part of this change, and I want to highlight this. And they are part of the next change. Basically, let's give an overview of the process of what's happening. So now we will have multiple threads that traverse basically the file system. So we have multiple producers. And the process itself, what are we doing? Again, we perform the first tier reader operation on the dir. If we found the dir, we process it. Again, files at this point will be ignored. And now the changes begin to manifest. If we find a dir, we have two options. Either we have a free worker thread, another free worker thread, and we identify it by keeping a counter of free worker threads. Then we queue the dir entry to a queue. So basically, prior to this change, we only had a file queue. And in this change, we will have two queues, one for dirs, one for files. And we will add the dir entry to the head of the queue in order to perform a depth-first search of the dir tree in order to minimize the size of the queue. And we will wake up the worker thread, and this worker thread will dequeue the dir entry and process it, which basically takes us back to step 3.1, which performs the reader operation. If we don't have a free worker thread, we will process the next dir by ourselves recursively. So basically what I described just now is the hybrid portion of the process, because we have a choice. Either we process the next dir ourselves recursively, or we add the dir entry to the queue, and this decision is based on whether or not we have other free worker threads. And the rest of this process is not changed in this patch. As I said, there is a follow-up change for this change, which deals with the file handling itself. So again, we will perform a second reader operations in which we will ignore the dir entries and we will handle file entries, basically queue them to the queue. And the termination mechanism of this process is based on the fact that once the entire file system has been traversed, all the worker threads except the last will be in a waiting state, basically waiting for a dir entry to be added to the queue. But since we finished traversing the file system, no more dir entries will be added to the queue. And this last worker thread will identify the situation again by examining some counter and basically terminate rebalance. Another thing that is still not changed, because we still have the file queue in this patch, is the consumer side of the things. Things are not changed at all. Again, the multiple threads, they queue the file entries and process them for migration exactly as it is in the original code. Some design considerations regarding this patch. If we are talking about the dir queue, we said that in this patch we'll basically add a dir queue. It's not possible to hard bound this queue because the threads that operate on this queue, both the consumer threads and the producer threads, are the same threads. So just say I have a queue with a limitation size of 1,000. It's not possible, because think about the situation where all the worker threads are currently processing some dir. They perform the reader operation, and all of them are trying to add entries to the queue. It's very possible that the queue will get filled, and none of them will be able to add entries to the queue, and they will wait forever because there is no other free worker threads to dequeue elements, so everything will basically hang. So this is the reason this hybrid approach, which I described, was chosen, because it solves this problem. And as an added value, it actually reduces the risk, let's say, for contention on the mutex that protects this file queue. So there is actually a benefit by it. And we can think about this dir queue like it's virtually bounded by the number of free worker threads. If I have 8 worker threads, then I can maximum add 8 dir entries to the queue. And as I mentioned, dir entries are added to the head of the queue in order to minimize the size of the queue and perform depth first search of the dir tree. That's it for the design considerations. And yes, I see a question, please.
Yeah, Bharat, I did not understand why we have to make 2 passes again, because if I understood the first design correctly, the first traversal is to do the fixed layout and second traversal is for the migration, right?
So as we said, there is no more fixed layout operation in the global layout.
But there is still even after moving to global layout, there are 2 traversals. I didn't understand that part. Why do we need 2 traversals?
So maybe this visual representation will help you understand the process itself. As I mentioned, there are 2 parts for this change. And I split this to 2 parts because the changes are quite significant, and I didn't want to overwhelm in the reviewing process. So if we combine the two sets of changes, everything that is related to the file queue will be completely eliminated because the migration responsibilities will be transferred to the multiple threads that process the file system. But all of this is not part of this change. The purpose of this change is just to transform the mechanism that traverses the file system from single-threaded recursive to multi-threaded iterative. So in this point, we still need the two reader operations because we still need the file queue. Does this answer your question?
So are you saying in the next part you are going to remove the first reader?
I will remove basically the second reader.
Yeah. Okay. Basically, one reader is going to go away after this patch. Okay, got it.
So in this visual representation, let's walk through it. We have the same initialization method that spawns the consumer threads. So this entire side of the process is not changed because we still have the file queue. But whatever happens, let's say in the code path of the main thread does change. Because we go now into a different method that initializes the multi-threaded traversal of the file system, which spawns worker threads. So basically, the job of the main thread is done here. At this point, the main thread will wait for the process to finish. And the multiple threads, the multiple worker threads, basically, this is their main loop, basically all of this. They will take some dir entry, perform a reader operation, either in a recursive manner or in an iterative manner, proceed to the next dir, and perform a second reader operation, again in a round-robin manner, which will queue dir entries to the file queue. And as you asked, this entire file queue thing will be eliminated. Let me actually jump a couple of slides forward. In the end, this is how things will look. So we have, we have just the worker threads, and basically we can call them rebalance threads because they perform everything, both the dir processing and the file processing. And their loop, yes, basically covers both of them. Well, let's say we perform reader operation and we have just one. If we find dir entries, either we add the dir entries to the queue or we process the next dir ourselves. This is what I described, the hybrid approach. But if we find file entries in this dir reader operation, we don't ignore them. We actually perform migration. So I think this answers your question, correct?
Yeah.
Okay. So I do
want to check on the time. I think there's still considerable amount of discussion is left, right? Do you want to set this up as another one, maybe on Thursday or something like that?
Let's ask the team. How do you wish to proceed with this? Do you want to cover the rest of the changes in another session? Because there is still considerable amount of content.
It will take 1 more hour, I think.
For me, no problem. For me, we can schedule another session for this.
Yeah, it would be great if you can schedule one more session.
So maybe let's agree on a time because I want to see a good attendance like we have now. So what time will be a good time for this follow-up session?
This time is fine. I'm like 2:30 to 3:30. The slot is fine. Day you guys choose. I personally am not available on Friday, but on Wednesday or Thursday, I'm like either tomorrow or day after is fine.
So I don't want to postpone things too much, like because I want the knowledge to stay fresh in your minds. So I'm thinking maybe Thursday at this time as well. This can be good for us, for the team.
Thursday I have a meeting at this time, so can we have it later in the day, like 5 p.m. or something?
Can you describe how further is this in relation to this hour? Because there is some difference between Israel and India.
Yes. So
It's like 2.5 hours after this time.
Yes, for me it's fine. If for you guys it's not too late, I have no problem with this. So yes, for the rest of the team, this is acceptable.
Yeah, it's okay
Yeah.
for me.
yes.
Okay, I will schedule a follow-up meeting.
Yeah, the difference is 3.5 hours now from Israel to India, but I think it doesn't make a difference.
Yes,
on
for
the
me it's
visibility.
fine. Whenever it's comfortable for the rest of the team, I'm flexible.
On your calendar, that social call is there now after that, generally, right? After
But
that,
you said 2.5 hours from now, so it
Yeah,
will.
I think I might have made a mistake. I think Choba was correcting. I think it's 3.5 hours. Is it
3.5
3.5
hours.
hours?
Yeah, it's 3.5 because of the daytime shift.
For me it's fine. For me, no problem. I think it should be around here.
on my
2:30 Israel time.
Wait, I'll just Google it. You can stop recording. I think it's fine.
Yes.
Let me just check.